All right, so now we are moving on to the next topic, which is going to be about physical properties. So physical properties of alkenes and alkynes are kind of similar, right? So they are all considered, for example, non-polar compounds, right? Because they contain only carbon-carbon or carbon-H bonds of some sort, right? So be that kind of like triple, double, single bonds, they are all still considered non-polar, right? So non-polar bonds. So, and then consequently, they will not be soluble in water, right? So they will be kind of like, as we call it, immiscible with water. So they will not form solutions. They will form some sort of separate layers, right? When you attempt to mix those hydrocarbons with the water. And they are less dense than the water typically. So unless you have some kind of like huge molecular weight alkene or alkyne, then conceivably it could be more dense than water. But again, the experiment will show, right? So who is right, your estimations or the nature? So if they're less dense than the water, then from here you can have an important takeaway. If they're immiscible and if they are less dense than the water, then they will float on top of water. Because why? Immiscible compounds that don't form solutions separate into layers by density. Lower heavier density, higher density will be lower, right? It will sink. Lighter density will float. So that's kind of like logical. If you think about some sort of, let's say, whatever it could be, some sort of material, right, from which coffee cups are made. It's very light material. It's like filled with like basically bubbles of air, right, which makes its density lower than the water. And if you throw this coffee cup into the water, it will float, right? So, because the material of the coffee cup is lower density-wise than the density of water. So density of the coffee cup material is lower than density of water. Consequently, it will float. So it will float on top. So we could say that higher density compounds will sink, right? Which is kind of logical. Heavy stuff sinks. So lower density compound will float, which is kind of also logical because the lighter stuff, lower density will float, right? So here is going to be like a similar principle will manifest itself when you try to mix alkenes or alkynes and water. So then of course, the boiling point, the famous boiling point. So density here is less than 1 grams per ml, right? So that's density of water, 1 grams per mil. So density of alkynes or alkenes will be less than this value. So, and then boiling point will increase, right, as molecular weight increases. So basically you will have a heavier compound, right, a larger molecule, more interactions between the individual atoms of those molecules, right, via dispersion forces, which we know are peculiar to nonpolar compounds. Consequently, the more atoms you have in your alkene or alkyne, right, higher molecular weight compound, consequently, the more interaction will be present between individual molecules of those huge compounds, right, from the molecular structure perspective. The more interaction you have between huge molecules, the harder it is to separate them. Consequently, boiling point will be higher, right? Because you need to overcome higher amount of intermolecular forces, right, that exist between individual molecules. So then that's what we can say about the physical properties here. So now let's move on to something more interesting, such as, what would you say? Chemical properties. Let's now take a look at the typical chemical reactions associated with the alkenes and alkynes. So, first of all, let's see what the general scheme looks like, right? So, by general scheme, I mean showing the functional group. So, such as in this case, we are going to be starting with the functional group of alkene, right? You see again, reoccurring things show up, right? So, carbon-carbon double bond. And then here we can have, maybe it's going to be 4 H's, right? So maybe, just now imagine, I cannot drop possibly all the alkenes, right? So But if you want, you can just substitute, switch this H to CH3 or methyl group, right? Maybe it's going to be methyl here instead of H, right? You basically kind of like remove this H and then you will switch this H to CH3. Single bond will still prevail, right? So instead of here, you can switch by the same token H to a propyl group, right? And then this will kind of force you to remember what's a methyl, let's draw that. What's a propyl, let's draw that. Kind of draw that, maybe even kind of like whilst you are in line to get some sort of omelette or something. So it turns out that this type of learning is kind of like continuous learning that spans over a period or long period of time is quite efficient as opposed to just cramming everything the night before the exam, right? So, but it is a tangent. So alkenes can participate in so-called addition reactions. So now we are going to add quite literally some sort of substrate, right? Substrate is another like fancy word for like a chemical reactant, right? So that can react at this double bond as we put it, right? So this double bond between the two carbons will be involved in the chemical reaction. So yeah, basically what's going to happen is that this bond will be broken and one of those bonds will be broken, right? So double bond, not a single bond here, right? But the double bond between the two carbons will be reacting, right? So reaction typically implies the breaking of some bonds and the making of the new ones as we obtain our product. So here we're going to break this XY bond, which is made of like two electrons, right? Like a covalent bond, typically, that's what we're dealing with in organic chemistry, is made of two electrons, right? So then two electrons. So this can be broken, and now you are going to have a free electron on X, free electron on Y. So same here, right? Carbon-carbon double bond, not the entire double bond, but only one bond of the double bond will be broken. This bond stays intact, right? So that's why, so I show the breakage of the bond with a squiggle line. Here you see the squiggle line crosses like one single bond. Here the squiggle line crosses only one bond, not two. It means that this bond is not touched. Don't touch it. So touch this bond. So that's what gets broken. That's what the squiggle line crosses. It only crosses one of the two bonds. That's one of the key things, right? So basically you can say a single bond inside a double bond is broken, right? So not the double bond is broken. So that would imply that both bonds are broken, which doesn't happen in this reaction, right? So then what happens next is that you are going to have to add X and Y, provided there are some sort of atoms, to the atoms of C and C. And then you will make CX and CY bond. So let's see what happens. So the following thing will happen. So you will have your C. So single bond, one bond prevails out of this double bond, right? It stays, kind of just redraw. That's the top bond. It's here, let's imagine. Those CH bonds will also prevail. Okay, great. So they will stay, right? And then you're going to make, so you see electron and electron get connected. Electron on C, electron on X get connected. You make a single bond. CX, new bond is formed. Same here, similarly. Now what happens here is the formation of the CY bond. C, electron. Y, electron. Two electrons make what? A covalent bond according to our previous general chemistry knowledge. So that's it. You have now CX bond formed, CY bond formed, right? So two new bonds were formed. Two bonds are broken, two bonds are formed in this particular example. So now let's take a look at some particular examples, right? So let's say, let's imagine that we are going to have now, we're going to look at just the alkene, right? So, and let's say I'm going to draw something like that, right? So what does that mean here? So you have a and. Let's say it is actually the condensed, not the condensed, but the line angle formula, right? Line angle structure. So this implies that this is a bond between carbon-carbon, and this is just not an empty space, right? So this is a dot. The dot represents a carbon. Carbon with one bond shown explicitly. Carbon must have four bonds, right? Consequently, there are three more bonds. we only imply single bonds, right? And we only imply carbons and H's. So this is a carbon with how many? 3 H's, right? So that's going to be CH3. That's another methyl. CH3 is also known as methyl. Methyl and methyl, right? So that's the power of condensed structure, right? Not just empty space, but in fact, there is something, right? So now we're going to do the so-called hydrogenation. We are going to add hydrogen to our molecule, so which means we're going to add the H2 molecule, and then it's going to be done at certain conditions, such as PT. PT is the catalyst here, right? So that accelerates the rate of this chemical reaction, and we're going to go from an alkene to the respective alkane. It's going to be the saturated compound. You see, we saturate these carbons with more hydrogens, basically. So that's what saturation means. So now single bond, only single bond stays, right? So these are our, let's say, methyls here, right? So we'll just show them as such. Then we're going to specifically add hydrogens, and we'll show them that we added those hydrogens. So that's okay to show it this way, right? For the explanation's sake. So basically now here we went from the sp2 hybridized carbons to only sp3 hybridized carbons. So yeah, that's it. So you also changed the hybridization from sp2, right, to sp3. So you went from the trigonal planar geometry for those two carbons to tetrahedral and tetrahedral geometry for these two carbons at which I'm pointing, right? So you made your alkane and you started with an alkene. Alkene becomes an alkane upon the reaction of hydrogenation. Okay, so next one is going to be, let's take a look at some, I guess, more examples, right? So we can also hydrogenate an alkyne, right? So that's entirely possible. So it's going to be a little bit different, right? So, but it's okay. So let's take a look at our alkyne example. Maybe it's going to be something like that. So let's just show some relatively like simple ones, right? So let's imagine that this is going to be like that, right? So this is going to be our line angle formula, in which case we're just going to have lots of implications, right? So here we go, right? So we show our carbons at the triple bond, right? So because we want to see that those carbons are involved in the chemical reaction, right? And then those could be, for example, let's just say that these are methyls. Let's show the condensed formulas for now, right? So it's a little bit more kind of like telling for our like initial exploration of the organic chemistry specifically. It's going to be quite useful, right, to show a little bit more detail. So, and then for your practice, you can show every single bond using the expanded structures, right? If you want to like kind of like figure out for yourself what the bonding patterns various atoms undergo, right? So you can at least do that, and then you won't be confused that, okay, how many atoms, how many bonds is an hydrogen atom supposed to make, right? So you'll not be having this question. You will know firmly that a hydrogen atom in organic compounds is supposed to make only one bond, right? Carbon will make 4 bonds total in various patterns. So then you will kind of ask the same question to yourself about nitrogen and oxygen, stuff like that, right? So here we go. So let's try to add hydrogen to here, right? So to this particular alkyne. So we can use, for example, partial hydrogenation. We'll only add one molecule of H2, right? So we'll break only one bond. So we'll make the CH bond and we'll make another CH bond. Okay, so let's show what happens, right? So that's going to be done on platinum as a catalyst, right? It's called or with the platinum as the catalyst being added to this reaction. So we are going to redraw what doesn't get into the reaction, right? So it doesn't mean that we're just going to forget about that, even if it doesn't participate directly in the chemical reaction. We need to redraw even the parts of the molecule that don't react, right? Still. So, and then we're going to show our product. So instead of triple bond, we're going now to have only double bond. The double bond will survive, right? So, and that's going to be something like this. So then this electron and this electron will be liberated because of the breakage of the HH single bond, right? So now draw the atoms here. next to the reacting carbons. Free electron and free electron, they will be liberated because of the breakage of this single bond, right? So free electron, free electron. Now you're going to make your new bonds. That's your new CH bond. And now you went from an alkyne to an alkene, right? So you used only one molecule or two H's, two hydrogen atoms, right? Total. So you can also add, theoretically, 2H2, right? So let's imagine you're going to have 2H2 or HH and HH, right? So you're going to break those bonds as well. Now you're going to engage this bond too. Guess what? You're going to make now not two new CH bonds, but you're going to make four total new CH bonds. So now that being said, this bond is broken, so these electrons are liberated. So we're going to erase this bond, and then we're going to show those liberated electrons, right? Top bond, top electrons. Now, these top H's are also released as atoms for our kind of like building blocks purposes. And now you have an alkane. So quite exciting. So this is going to be the hydrogenation reaction, right? So now let's move on to the further reactions, which will be the addition of the halogen or halogenation process, right? Halogenation process can be done both with alkenes and alkynes. Again, so we will have a relatively simple alkene for our intents and purposes, which is going to be looking like this, right? So that's going to be our alkene, let's imagine, right? So we are going to show the condensed formulas for now. So they're relatively fast, but also they kind of provide a good plethora of details. So now we're going to add, for example, halogen. What could that be? Bromine, right? So molecular bromine. Molecular bromine is added. So now we're going to break this bond, electron, 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 electron. Connect CBr with electron, electron, and another CBr with electron, electron, right? So what do I mean by that? So I'm going to redraw what is not participating in the chemical reaction, and then I will like supplement it with the new molecule. So CH, these ones stay, right? This bond is broken. Now you have the liberated electron, liberated electrons, right? And then here you go. So that's your new carbon-bromine bond, right? So now you have the essentially alkane, which is a substituted, right? Substituted alkane. So theoretically, that could have been a couple H's, right? So, but instead of them, you have couple bromines. So you have a substituted alkane or brominated alkane, right? So it could also be called, yeah, I would say it looks like an alkane because you don't have any more like all the carbon-carbon double bonds, right? You only have your carbon in sp3 in the state of sp3 hybridization surrounded by single bonds, right? So those are sp3 carbons now. So there is no more carbon-carbon double bonds. So it is going to be technically an alkane with several, like two halogen substituents, right? Non-alkyl substituents. All right, so now let's maybe take a look at an alkyne example, right? So how this guy gets halogen added to that. So it's going to be like quite a simple alkyne, right? So like this. So with just a couple methyls on each sp carbon. You can use the terms, right, to describe those things, like using your like newly learned scientific terms. So maybe we're going to add, let's say, chlorine, right? So chlorine to molecular chlorine is added. So then you're going to get this. So this bond will be broken. You have three bonds. One will be broken, and then draw electrons on each bond. See what's going to happen? So it's going to be now an alkene, right? Substituted alkene. You have the carbon-carbon double bond, right? And then here you have a substitution, right? So that's your alkene. So you're going to have chlorine and chlorine. You make two carbon-chlorine bonds by virtue of those electrons. Electron and electron, electron and electron. Here they are. You can track them. Like if you look at the dots and how they are connected, you're literally connecting the dots, right? So Quite interesting. So that's the Cl right here. So you can add 2 chlorine molecules, 4 chlorine atoms total. You will engage another bond, and guess what? Only one bond prevail out of those 3. This bond will be gone, right? And then instead it will now liberate couple electrons to connect to couple chlorine atoms. So that's it. Now this is going to be your substituted alkane, right? Because all those carbon atoms are now, this and that one are sp3 hybridized, they're tetrahedral, right? So with the respective geometry, and that's it. So, and then they can be, this compound can be considered as substituted alkane, because instead of those theoretical H's here, right, you have chlorines, right? So you substituted your H's to chlorines with chlorine substituents, right? So this is kind of like the tight connection between all those terms.